Okay, so I think, my understanding was that this is supposed to be, a quick discussion where kind of everybody participates and we try to think about some of the things we learned yesterday, in particular from the hardware session. So please feel free to chime in and hopefully this will be a good discussion. So for those of you that don't know me, my name is Ian Bratt. I work at ARM on machine learning hardware and on other aspects of machine learning within ARM. Very much a hardware person in the past. So first of all, I thought it was just like an awesome session yesterday. I think just really, really high quality stuff. And we really saw kind of the full spectrum of how tinyML is impacting the hardware world. So, we saw a great talk from Simon around enhancements to very established architectures. So this is, moving the needle on these established architectures, changing them is very difficult because you're moving an entire industry. And so we're seeing ML kind of shape that already, which is pretty cool. We're seeing new state-of-the-art startups with very cool digital acceleration. So I think the GreenWave stuff was very interesting, and I think it shows it's a great example of the new sexy startups that we're seeing in this space. And I thought that was super cool. And we're trying to see also what it would take to integrate some of these even newer types of acceleration. I thought. The in-memory compute, for the last 2 years, a lot of these in-memory compute companies have come through ARM, and I'm like, wow, this is super cool. And then I think at the system level, how do we start reasoning about integrating these in a system? How do we program these things? And I thought the talk yesterday from Naveen really did a great job of starting to flesh out these challenges and show how maybe there is a path forward to integrating some of these exciting new acceleration technologies. So that was really exciting as well. And then of course, we saw really kind of the optimal solution. So full co-design, if you've got all your data and can redo your network and really do a joined hardware software solution, cascaded networks, what's really the optimal thing? How can you really take it to the very end? And I thought that was exciting. So we really saw this full spectrum from established architectures all the way to kind of really pushing the theoretical limits of what you can do. And that's just super exciting to me. So I think, I'm a hardware guy. I've worked on CPUs, I've worked on memory systems and GPUs. And frankly, 3 or 4 years ago, things were getting kind of boring actually in hardware land. And then machine learning came along and it's just like, there's no shortage of ideas. So, my team and everyone I talk to, everyone's got all these, crazy ideas. We'll do new floating point formats, new compression technologies, all these new exciting things. And it is awesome. It's like being young again. I love it. But there's a big shortage of ways to unlock and use these ideas. And that's what really came across to me yesterday. So if I look so there's all these cool hardware ideas, and then I think of, okay, how am I actually going to use them in a real system deployed in the wild to make money? Like we're all actually at the end of the day here to build stuff to make money, most of us. So the software ecosystem is a total Wild West. If you look at it, it is so fragmented. And just to be perfectly transparent, I think it's a bit of a land grab at this point. We've got all the big players, Amazon, Facebook, Google, everybody is pushing their frameworks. The hardware guys are pushing their frameworks, and it's a land grab, and it's the Wild West. Now that's exciting because it's very dynamic and it's changing every day. But it makes me think as a hardware guy, if my end goal is to get these cool new things out there, how am I going to actually use them? So, as a hardware vendor, what are we supposed to do? So from the hardware perspective, how do I know what to build so that I can actually get something out there that lots of people will use? And that's the big takeaway that I took from the session yesterday. And I think it was echoed a bit when we learned about some of the different hurdles folks have had to go through in order to deploy models on the edge and kind of the state of the art in that area. So I think this is very, very interesting. And I'm interested to hear the thoughts. So Naveen, are you here? No. So, I saw that your group had done some software work in order to kind of get your prototypes working. What was the experience like? What do you think this space looks like?
So first of all, I really agree with you that whoever's doing hardware needs to think about who's going to program it other than the grad student or engineer who hardware, which is where all of a sudden the problem becomes really real. And so I think, the way that we do research in academia and probably the way that we do research in industry as well needs to adapt so that those groups that are building not just the software frameworks, but also, the people who are using the software frameworks, the data scientists who are coming up with these models that they think are cool, but then, there's some pitfall on some system level, down the stack. I think those groups, those barriers need to really sort of be broken down. So I think, what does it look like? It's challenging because it's a different skill set, but I think it's the kind of thing that, with everyone committing to these sort of totally new, awesome ideas, we can sort of come together and do some of this stuff. I do think it's the wild, wild west. I think that there is some really enabling sort of standardization that's happening. I think the hardware people are grateful for things like Onyx and stuff like that. And the more that we can push that, I'm looking forward, in fact, to talking to the Microsoft people who did the L and indeed, the Tiny or the TensorFlow Lite folks to figure out what are the ways that we can intersect all of this infrastructure at the different points at which it's most needed so that the barrier for any group is as low as possible to deploy that full platform, which includes the software system. Right. Is that?
So I think standardization and kind of just, I think you also said something that was interesting is kind of getting the cool ideas out there might provide pull, in a sense that if we get that out there, the proof of concept is there, then people will say, oh yeah, we really want to unlock that. So let's work together to unlock it. Yeah, I thought that was interesting. Okay.
So Danilo Pau from ST Microelectronics. I do appreciate your slide and the subject. I just wanted to say that in Italian, we would call this not Wild West. We would say casino. That's not a normal situation. It's a casino, I mean. Look, I don't know how many deep frameworks are out of there. Okay, I don't want to list them. Compilers. I just realized that there are at least 4 compilers for AI. And at least 2 years are needed to develop one single chip. And who should use those chips are normal embedded software engineer. Normal, not data scientists. Right? So all in one, these guys are certainly scared. And so will not work on that because it will take years for them to learn just one chip. Imagine if they want to change the chip on another solution. So I think the real opportunity for this meeting is start to think first to stabilize the software interfaces. Yeah. Second, to invest on interoperability. A standardization committee first should work on interoperability. Yeah. I mean, build together people and use a common language.
Yeah, yeah. So stabilizing interfaces, standardization. Another point I want to make, I think just made me think of it from the last 2 comments was, a lot of the proof of concepts, that might be done by a PhD in physics, super smart hacker, right? And we need to enable anyone, anyone that's got some data to be able to create a neural network and deploy it on the edge. And it's a very big difference between those two in terms of appetites to kind of roll up their sleeves. So yeah, I think it's standardization around stabilizing software interfaces and that.
So on that topic, I just want to give a bit more context because we hear this constantly from the hardware side is, oh, please just standardize, just fix your specifications, tell us what you need. And from the software framework side, we actually turn around and blame the researchers because they're constantly changing the operations they actually need. They're constantly changing the architectures. They're constantly discovering new things about things like quantization and like weight compression formats. And that is where a lot of the challenge of standardization comes in. It's not kind of like image formats where there's just kind of a bunch of different formats that all hold the same kind of basic information. There's all of these different semantic things that are emerging constantly that we have to kind of keep up with. And, you know, to be honest, I don't see much of a future over the next few years for any accelerator that isn't able to have some, even if it's a fairly slow callback, to run general purpose computation, even on like, you know, it's the equivalent of a little microcontroller that's like very close to the accelerator, so that it can handle, oh, here's this new op, or here's this new activation function, which people have just discovered. Because if you just standardize on the things that people are using today for a chip 2 years from now, it's unlikely that those same, you know, that people are going to have different operations that they're bringing to the table. So not to sort of like pass the buck, but, you know, part of a big reason that it's a Wild West is because the research side is still changing so fast.
More than exercise.
Yeah. So, I mean, I want to reinforce what Pete said. So, you know, those researchers that are making this churn. So I think that I'm one of the representatives of those, at least in my company. So I manage the machine learning research group in MSRAI at Microsoft. It's not, the researchers are still thinking about it. This is going to go forever. So this will never stop. So that's what we do. And we're very, very far from where we think we should be. I don't think we're going to get there in a year or 2 or 3. It's just going to keep changing. This, by the way, is one of the reasons why, you know, whereas other companies are investing in TPUs or in large GPU arrays, Microsoft's big bet in the cloud was on FPGA. I don't know that it's a good bet. I'm not saying that it's correct, but this was the reason that the realization that it's just going to change and change and change, and we need to have that flexibility. So that's why they did it. I mean, it wasn't me. It was my decision. But that was the rationale. So it's not gonna stop. And I don't know, we need to kind of learn to deal with it, build the right abstraction layers to enable hardware and innovation and machine learning innovation to coexist. The thing that worries me more, so you were talking about interoperability. I'm worried a lot about safety, and with these hardware accelerators, you multiply 2 matrices once, and then you multiply the same matrices again, you get a slightly different answer. And that really, really scares me. If we're going to put these devices, these AI things in our bodies and healthcare, if they're going to drive our cars, if they're going to fly our planes, and the manufacturers of these products that are going to use these accelerators don't really know what's happening under the hood, that's really terrifying to me. And what I don't really understand, and maybe you can tell me, is how do these open source hardware platforms come to life? Like a RISC-V and things like this. If there was an open source specification for these hardware accelerators, it would be much easier to get them certified, to get the health people to certify them, the FAA to certify them, to put them in planes and so on. I don't understand the sociology of how open source hardware works, but I think there's at least for the safety and compliance issues, there's a dire need for that. So
right. Yeah, I don't know if I'm qualified to talk about the sociology of open source hardware, but I think the big point there is so one, you're saying that actually things will keep churning, right? So to be pushing for standardization, maybe it's too early, and maybe that's okay, but you're also echoing actually what's really important maybe is just putting some compliance in place so that a researcher is sure that what they're doing up here, they will get the same experience on the edge, and it's very rigorously tested, et cetera. So kind of maybe a compliance standardization might be a first step.
Very beginning, TensorFlow, the software stack, you can look inside and see what it's doing.
Right.
And I think that, you know, similar accountability may be required of the
Right.
of the hardware.
Well, do you think the open source is required, or I mean, there's other ways to get compliance, right? Like, so GPUs are all very close source, but there's very rigorous compliance testing at the GPU level so that you get the same experience when rendering 3D scenes.
Yeah, I mean, I don't know. For me, open source allows, if you're going to build something on top of my thing, and there's
Right.
dark magic in there, there's voodoo and hacks.
Right.
At least you know what they look like.
Oh, yeah, so
I just want to contribute one thing to this discussion. It's a very interesting suggestion about open source AI acceleration, but I think the big difference is that open source cores and compilers and things like that are based on technology that's about 60 years old, right? And it's stable, right? There's control code and how to optimize load store architectures, things like that. That's a very standardized recipe, if you like, where AI is changing, is changing year to year. There's many different ways of doing things. And the accelerators is also one of the tricky things why it's difficult to write accelerators, because what works today might not be applicable in another year or two. And so it just makes it difficult. I mean, it's a very interesting idea. I guess eventually we'll get there.
So question is that for AI, and this is probably an example of like, can industry sort of decide that there is a set of benchmarks that needs to run and provide certain acceptable accuracy, like this stuff that we are trying to do in MLPerf, for example. Yeah. Is that something that ought to be sort of embraced industry-wide, so that irrespective of what hardware you have to meet these benchmarks with certain performance level and accuracy level, and at that point maybe it can be certified.
Right, I see. So I guess there's different spectrums of compliance. There's the bit accurate compliance, where if I run on this platform, I get the exact same identical bits on this one. There's other in terms of like accuracy compliance, where you specify the suite. Yeah, I think that's an interesting idea.
And just, sorry, not to, but like that's actually something that Google is super interested in. Like, we put out the speech commands data set specifically so that we could actually start to get standardized kind of benchmark for our like voice wake word stuff. And we're looking at doing something similar with the visual wake word. And it's much less about, with that, it's much less about, hey, here's the software, like that's separate from the TF Lite stuff. That's more like, hey, let's just have a standard data set and a standard problem out there. And then we can actually evaluate all of these different solutions based on like using the same metrics. So I think that's really important for us from the software side too.
Okay, last one, Naveen.
So I think these are like really good comments, and I think that they point to basically the following. What we have here is like the proverbial chicken and egg problem. And I think that benchmarks don't solve the usability and usability confidently problem. What benchmarks do is they allow me to compare an architecture. And I think the usability and usability confidently problem, whether it's reliability, whether it's portability, all points to the same thing, which is that we need very robust functional specifications of whatever level of the system stack you live in, whether it's hardware, whether it's some low-level code, or it's any other point. And so I think the thing that we need to really focus on, though it often doesn't have the same glory as focusing on the other things we focus on, is creating those really robust functional specifications. And then from there, having them at enough levels that wherever your expertise might be, or wherever someone who's not in my group's expertise might be, that person has an entry point into the rest of the sort of stack. And so I think we need to go like hyper drive on creating very robust functional specifications with as much granularity down the stack as possible so people can get engaged. And I think that's where there's a lot of research questions, frankly, but the group that's best positioned to tackle those research questions is this group.
Right. Well, thanks everyone. That was a great discussion. Really enjoyed that.